How do you interpret probability in Dirac notation? Imagine you're trying to predict the outcome of a quantum experiment. How do you connect the math to what you actually observe? That's where Dirac notation comes into play. It's a simple yet powerful way to describe quantum states and their measurement probabilities. In quantum mechanics, the state of a system is written as a ket, which looks like psi. Think of this as a container holding all the information about the system's condition. When you want to find the likelihood of measuring the system in a specific state, say phi, you look at the inner product between phi and psi. This inner product, written as phi psi, is called the probability amplitude. It's a complex number that contains both magnitude and phase information. To find the actual probability of measuring the system in the state phi, you take the modulus squared of this amplitude, which is written as phi psi 2. This squared value is always a real number between 0 and 1, representing the chance of that measurement outcome. Now, the state psi must be normalized, meaning psi psi equals 1. This normalization ensures that the total probability of all possible outcomes adds up to 1, just like in everyday probability. When you perform a measurement, you're essentially projecting the state psi onto the state phi using a projection operator, written as phi phi. The probability of this particular measurement result is then given by the expression psi, phi phi psi, which simplifies to phi psi 2. This approach extends naturally to systems with multiple possible measurement outcomes, where you sum the probabilities for each orthogonal basis state. For example, in a 2-qubit system, you might have states like 10 or 11, and the probabilities are calculated similarly using their inner products. In the realm of quantum technology, Dirac notation is the standard language for describing states, operations, and measurements. It helps scientists and engineers write down complex quantum algorithms, error correction methods, and communication protocols in a clear, compact way. So, understanding how to interpret probability in Dirac notation boils down to recognizing that the probability of a measurement outcome is the squared magnitude of the inner product between the state you have and the state you want to measure. This simple idea is the foundation for predicting what happens when you look at a quantum system and is essential for designing and understanding quantum technologies.